Welcome back to our lesson practice review, where we are close to wrapping up chapter 3 with our lesson 11. We really focused on what we call the remainder theorem in this lesson. We've already talked about a couple different things about how to find if something is a factor. We've made sure that if we do division and we get the remainder of 0, we know that if we were to see where the x-intercepts are at, that would also tell us that it's a factor. And then the remainder theorem is the one that states that when you have a factor, that means that if we plugged in the number that we're subtracting, it would make the equation 0, right? So for example, below us here, we see that we have x minus 1 and x plus 2. We're going to check if those are factors of f of x here. The way we do that is we look at, hey, what makes this 0, right? Which would be positive 1. So we try plugging in 1 to see if we get 0. Whereas this one here, the x value that would make it 0 would be negative 2. So when we plug in negative 2, we end up getting 0, which tells us that x plus 2 is a factor. So for number 1 here, is x plus 3 a factor of f of x? And to do this, I'm just going to plug in negative 3 and see if we get 0. If we get 0, then yes, it's a factor. If we don't get 0, then we know that it is not a factor here. So as I'm going through this, 3 times 3 times 3 is 27. This also ends up becoming 27 minus 30. Oh, I have some negatives that I'm making mistakes on here because we have minus this, and then plus 30 because a negative times a negative, plus 24. This here becomes negative 54 plus 54, which becomes 0. So f of negative 3 is 0, which means yes, x plus 3 is a factor. For number 2, x plus 1 is a factor of g of x. Select all the other polynomial factors. And if you remember, there's multiple ways we could do this problem. We could do the remainder theorem. We could do what we know about division and getting remainders from that. There's a lot of different ways of doing it. It's kind of tricky because there's 8 different numbers that we would have to plug in here to try and solve each of them. If I'm told that x plus 1 is already a factor, I'm actually going to go through and I'm going to divide them to see, what's left over and kind of just work with what's left over here. It's not required, but I think that first of all, it gives us some good practice on division here. And also we basically then can use like an easier expression to kind of help when we're doing our remainder theorem in that. So this one, negative 4x squared, negative 37. Is that right? 37, 1, 2, 3. Okay, yeah. And then this becomes negative 37x. And then this has to be, what is that? 40. Yep. Okay, that all tracks. And then we got 40 again. So really, if I were to factor this with the x plus 1, what would be left over with x cubed minus 4x squared minus 37x plus 40. And so now, like when I'm plugging in these numbers, I could plug it into this whole thing, g of x, or I could just plug it into this more simplified version. Up to you how you want to kind of tackle this. You could go through, and then for this one, we plug in 2, then we plug in negative 2, then we plug in 8, then we plug in negative 8, and like you're just kind of going through to kind of check to see. Every time that you do find a factor, though, you could continue to divide to give us a simpler number to go through. So for example, the first one, if I were kind of going through, that would end up working for me would be if I plugged in 8 here. And I will show you how that works. So again, the numbers get a little bit ugly, which is why I recommend we start kind of dividing as we go and dealing with what's left. But basically here, what we end up getting, so we get these really big numbers that when we kind of multiply out and subtract them, we end up getting, if we were just to plug this into a calculator, we end up getting 0. And so what that means is that now I can divide x minus 8 from what we have left over here that I have underlined here in green. So now I'm just going to divide that by x minus 8 because I know that it's a factor. And so when I do that to the side over here, again, I have another box that I'm dealing with. Could you use long division? Totally. X minus 8. And then again, the nice part about this is that we're now just dealing with what was on the top of this one. So first term, first box. This is x squared, negative 8x squared. This has to be 4x squared. 4x, negative 32x. I have to add to negative 37, which is 5. Negative 5x. That becomes 40. And again, having 40 on the bottom there is good. So what we recognize here is that once we divide it, we're left with that on top. So I'm going to kind of scroll back and forth here. So I have x plus 1 because that was the one that we were given, x minus 8 because I used the remainder theorem, and now after dividing both of them, x squared plus 4x minus 5. Now again, at this point, I've said like, yes, C works, and now I have to like go through and find all of the remaining ones. Well, I could, yes, continue to plug 5 more numbers in and do this whole process over here, or I could just factor it, which would make things a little bit more simple. First term, first box, last term, last box. That middle term, 4x, needs to split up into two things that multiply to negative x and 5x. And then what that does is it gives us my final two factors. Sorry, let's get a little messy here, of x minus 1 and x minus 5 here, which is, x plus 5, my fault. Right here and right here. So I end up getting my 3 answers. Again, could you just like churn and burn, plug those numbers in? Yes, but there are ways that kind of expedite that or allows you to use algebra to make it a little bit simpler. I guess I call it simpler, but then I have all this work on the side here. But again, there's a way of doing it. Problems 3 and 4. Here's a graph of the polynomial function h of x. What is the remainder when h of x is divided by x minus 1? Well, again, that's like if we plugged in, we plugged in x equals positive 1 into the equation. Well, we see if we plug in positive 1 here, we get an output of negative 1. For 4, what is the remainder when h of x is divided by x plus 3? Well, that would be when we plug in negative 3, that will end up giving us our remainder here of 0. So really, again, what we know about the remainder theorem is that if we plug in, the number that would make this 0, it will spit out what our remainder would end up being. Number 5, what is the remainder when this function here, or this expression here, is divided by x minus 3? So again, I think it's obvious now that I personally prefer the area model when I'm dividing. Could you do long division? 100%. But you'll see mostly for me going forward that I'll continue to use the box just to get the same thing being practiced over and over again and to be consistent. X squared, negative 3x squared has to add to 7x, so it's got to be 10x squared. Negative 30x, so this has to be, what is that, 19x? Oh boy, this is an ugly number. So 19 times negative 3 is negative 57. And so what I need to add to this to get this here would end up being 60. So my remainder here is 60. Could I have done this an easier way? Totally. I really should have, especially due to this. I think I was just in the zone to divide, but really the faster way of doing this would be to plug in 3, right? So 3 to the power of 4 minus 5, 3 to the power of 3 plus 7, 3 to the power of 2 minus 11 plus 3. So I guess I was in the zone to divide here, but if you plug in positive 3, you'll end up getting 60, which again would be our remainder if we did the division. Number 6, if x minus 2 is a factor of j of x, what is the value of a? Okay, so this one's a little bit tricky. I'm going to use what I know about the remainder theorem is that if I were to plug in j of 2, that would give me 0. And so 2 to the power of 4 minus 3 times 2 to the power of 3 plus a times 2 squared minus 16 times 2 plus 14 is true. So I'm going to go ahead and simplify this. 0 equals 16 minus, what is that, 8 times 3 is 24 plus 4a. I'm going to switch these around because this is now my constant. Minus 32 plus 14. We'll start to add and subtract things over here. So this ends up becoming, what is that, negative 8 plus 4a. And then these two things become negative, what is that, 16, 17, 18. So 0 equals negative 8. Combine like terms to get negative 26. Oh man, this is also going to be an ugly number. Plus 4a. Add 26 over to this side. Divide both sides by 4. So I get a is equal to 26 over 4 or 13 over 2, which not the prettiest answer, but definitely what we got. All right, for number 7, create a polynomial p of x that makes this true. Okay, so in this one here, I think I'm going to be using the box, knowing that like I get a remainder here of 5 on the outside. So x minus 4 is in here. I'm multiplying, so 2x squared, and then 3x, and then negative 1. Those are the two things that I'm multiplying together. And then I actually just multiplied out. So 2x cubed, negative 8x squared, 3x squared, negative 12x. This is negative x, and this is, 4. And so now I'm just going to add everything inside the box here, which becomes 2x cubed minus 5x squared minus 13x plus. And I add these together to get 9. So that would be p of x. That would, when I divide it by x minus 4, give me that answer. All right, spiral review, problems 8 through 10. Determine the zeros of each polynomial function. So this is going back to one of our lessons from chapter 3 that allow us to use what we know about factoring and our box to help us. Going to definitely run out of space here, but I will try and fit it in as best I can. First term, first box. Last term, last box. Middle term of 5x squared needs to multiply to negative 14x to the power of 2. So that would be 7x squared and negative 2x squared, which means that this x squared, 7x, oh, sorry, just 7, my fault, and then negative 2. So when I factor it, it becomes x squared minus 2, x squared plus 7. And so when I'm solving that, I'm going to erase this to give myself some space. Now I'm looking for zeros. I'm not necessarily looking for x-intercepts, so I'm actually just setting this equal to 0. And again, I'm sorry about the space here, but add both sides, add 2 to both sides, take the square root of both sides, which gives me plus or minus root 2. This side, I subtract 7 from both sides, take the square root, x equals plus or minus I root 7. So some ugly answers here, but I guess I'll write them in the actual spot for my answers here. But I get root 2 plus or minus root 2 and plus or minus I root 7. All right, number 9. We have a difference of squares. So this becomes x squared plus 9, x squared minus 9, which gives me another difference of squares here, which is x squared plus 9 times x plus 3, x minus 3. When I set each of those equal to 0, x squared equals negative 9. Take the square root of both sides and get plus or minus 3i. And then x plus 3 equals 0, x minus 3 equals 0. And I get my solutions of x equals plus or minus 3i and x equals plus or minus 3. Now number 10, I'm going to use the box to help me with this. Hopefully it works out because there's 4 terms here. First term, first box, last term, last box. And then the middle 2 terms go in my remaining 2. And we'll see here if this actually works out. So this has to be x squared and x. This has to be... Oh, it doesn't work the way I want it to. So we're not going to use the box here. But we're going to use something that we've learned from this lesson, actually, a pattern that we maybe have seen as we've worked. But for example, let's look at number 2 here, kind of our challenging question that we went through. One of the main things to really realize here is that our last term here of 40, that has to be that last number multiplied together of all of my factors here, right? So when I kind of go through and when I factored it all the way, all those final numbers have to multiply to get the constant if they're all equaled out, right? Because 1 times 5 times negative 8 times negative 1 gives me 40. The reason that that's kind of helpful in this case is because my last term is 25. Oh, I went too far. So I'm going to see here if I can divide it by x plus 5. See if, negative 5 would be one of my solutions. So in this one here, we got first term, first box, last term, last box, and we'll see if it kind of comes out nice and even here. So 5x squared, that's got to be 6x squared, 6, 30, what is that, 30? Oh, that's x, my fault. 30x, and that has to be 5x, which, okay, yep, that works. So when I factor this, I now have x plus 5, x squared plus 6x plus 5, and now I'll factor this with my diamond and box. First term, first box, last term, last box. 6x has to be broken up into 2 things that multiply, which will be 5x and x. And so my solutions here, so I factored it and I get x plus 5, and x plus 1. And so my solutions here are just whatever makes those 0, which would be negative 5 twice. So it's got a multiplicity of 2 and negative 1. Because again, this is like x plus 5 squared, and then x plus 1. A little bit tricky one on the number 10 there. And then the last one here, here's the graph of r of x, a 4th degree polynomial. Write an equation for r of x. So we're not given any y values, so we don't have to worry about any vertical scaling. But if we're going to call this r of x, it is positive because my right side is pointing up. I see that my zeros are going to be at negative 5, 4, and 0. And then this one has a multiplicity of 2. So I'm going to do x squared, x plus 5, and x minus 4 for my equation. A couple tricky ones there on number 11. As we wrap up chapter 3 in the next lesson, we are kind of combining a lot of the stuff that we have now learned. So definitely got to keep an eye out for some of those tricky problems as we go forward.